Okay. So we were talking about the equations we can write. Okay, so here when we say compute dV and Reynolds, we compute them from equations of the flow, which are continuity, energy equation. What is the energy equation? Energy equation, which is also called generalized Bernoulli equation, is if you want the Bernoulli equation in a general form. So this equation will account for losses and will account for if you have pumps or turbines in your system. And we'll see in detail how to write. Okay? So always keep in mind in such problems to write the continuity equation, to write the energy equation, and then you will use these relations to do your iterative process. Okay? Now, this iterative process requires the Moody diagram because whenever you do a gas and from your equation you compute dV and Reynolds, you can verify if your guess was right or not. Because when you use Moody, you can get the friction factor. Now, the new friction factor you get should be compared with the guess you did. Okay? If the difference is lower than 10%, you can consider that I can stop. My solution is converged. In case no, it's not the case, we should repeat. We keep repeating until reaching a difference between the guessed value and the computed value that are close to each other. So always, if you want, each iteration will give you a new value. You compare it with the previous iteration, and then once you have a difference, a relative difference between the two smaller than 10%, you can consider that you have reached the solution. So we'll practice a lot on this in the problems. Okay. Now, what if what if the duct is not circular? So we said that Moody diagram is developed for circular ducts. We have shown that, okay, by experimental studies, we have shown that the Moody diagram can be extended also to non-circular pipes and ducts. All we have to do, okay, is to replace in Reynolds number. So you know that Reynolds number is rho Vd over mu. Okay, and we have that epsilon is over d. So the diameter is a very important parameter in the Moody diagram. In case we have a non-circular pipe and we want to use Moody, the experience shows that it is feasible. Just we should replace d, but what we call the hydraulic diameter, which is a parameter related to the geometry of the cross section we have. For example, if you have a rectangular duct, okay, a rectangular duct is characterized by h, the height, and the width. How we can compute the hydraulic diameter? The hydraulic diameter is equal to 4 times the cross-sectional area over the wetted perimeter. What do we mean by wetted perimeter? It is the perimeter in contact with the fluid. So if you have a rectangular duct, for example, the perimeter in contact with the fluid is this one. Okay? So this is the wetted perimeter in contact with the fluid. It's equal to 2h plus 2 omega. Okay? While the cross-sectional area is this area is equal to h times w. So the expression of dh for a rectangular duct, dh is 4 times omega h over 2 times h plus omega. Now, sometimes they say we have infinite plates. If we have infinite plates, for example, this means what? This means that omega tends to infinity. If you have infinite plates, what will happen is that you can neglect h with respect to omega when you do h plus omega. So in case it's infinite plates, you can simplify to the following. 4 omega h over 2 omega, and then omega can be simplified. And you can say that the hydraulic diameter for parallel infinite plates is 2h, 2 times the height. Okay. Now, in case it's not infinite, you use this formula to compute the h. Okay. So this is to tell you that the Moody was shown to be general, a very general diagram, because not only it's restricted to circular sections, but it was shown also that it works well. Of course, it will not work in all conditions. In general, we specify in which conditions it will work. So they can tell you for hydraulic diameters in this range, it will work. Okay. If not, if it's not working, we should develop a diagram for each section. Yani, we should perform experiments again to be able to draw a new diagram to be specific for the geometry you have. Now, we talked together about the energy equation. What is the energy equation? If you remember, we have introduced it last time. The energy equation, or general Bernoulli, states that the pressure head, okay, HP plus, if you want, let us write it first. So what is the pressure head? It's P over rho G, okay, plus, in Bernoulli equation, the second term is the kinetic term, yani plus P square over 2G, plus, you know that the hydrostatic head is just plus Z, okay? So in Bernoulli equation, we say that this is a constant, okay? This is the Bernoulli relation that you are familiar with. Now, in a general case, it's not a constant. It's not constant. We should account for losses, okay? So the general equation states that P1 over rho G plus V1 square over 2G plus Z1, okay? Now, now, if you have a pump, for example, the pump will increase the energy of your outlet. So you can add here plus H pump, because a pump will increase the energy of your system. So you can, it will be added to the initial energy. Equals to, from the other side, you consider all losses. So if I have a turbine, I will lose energy. So I put H turbine. And of course, I have friction losses. So I have plus H of total of due to losses. I will tell you why I put now H total, okay? Plus P2 over rho G. Sorry, 1 second. Okay. So plus P2 over rho G plus V2 square over 2G. So it's the same, it's the equation you are familiar with, but it's modified. It's modified to take into account losses and heat additions during for a general process, okay? And for example, here, if you consider a system where you are moving from, so I will remove the equation to talk more about the terms, okay? Look, if you are moving from 1 to 2, okay? You cannot say here that I can apply Bernoulli, because if you remember, what was the condition for Bernoulli? The conditions for Bernoulli is that no losses, and no friction, and no pumps or no turbines. So nothing should disturb the streamlines, okay? Which is not the case here, because first we have a pump, and plus friction cannot be neglected. because especially in pipe system, you cannot neglect friction because you have long distances and you have a lot of fittings. Each fitting in your system will lead to losses. What do we mean by fittings? Fittings are devices or connecting pipes, or it can regulate the flow in your system. And for example, valves are used to regulate the flow in your system. So you have different types of valves: open globe valve or half open valve. This is to control the flow of your system. This is a on-off valve, or so it's or completely open or completely closed. This is a valve that you can control, and you can change the percentage of the flow rate with it. So each valve, when you put a valve in your system, it will lead to losses. And these losses are computed also experimentally, and we have tables for them. And we will see together that I will give you tables telling you if you have an open globe valve, this is the friction coefficient of it is K. What is K? We define, look, we have two type of losses, major and minor, okay? What is the difference? Major losses is related to losses in a certain pipe, okay? So if you are moving in a pipe segment, the segment is of length L and is characterized by a diameter D, okay? And I can calculate a friction factor from Moody diagram. So I can say that HF, as we defined before together, the friction factor in this case is the friction loss is the friction factor times the average velocity in the duct over 2G times L over D, okay? So in order to get major losses, you need to know the length of your pipe, its diameter, and the friction factor, which you can get from Moody diagram. Now, what about fittings? So here, for example, where we have major losses, where we have minor losses. For example, in such case, if you want to calculate major loss, you should consider each pipe length. So here your pipe length is divided into several parts. It's not a one piece, have several parts, okay? Now, what is nice here, and we are lucky that the diameter is not changed. Since we have same diameter, okay, this means that we'll have same average velocity, and the velocity average at any cross section is the same because of continuity, okay? From continuity equation, if the cross section is not changing, so because you know that V average of a cross section times A equal times rho equal to m dot. In this, for study applications, m dot in equal m dot out, so the mass flow rate should be uniform everywhere. So in case the cross section is not varying, so V average is not varying, then I can consider that I have one friction factor in all of these pieces, okay? And why? Because Reynolds is not changing. Of course, I should have same roughness also, okay? So in case all pipes here, all pieces are characterized by same roughness and same diameter, which will induce same Reynolds from continuity equation, I can use one friction factor for all of these parts, and just L will be the summation of all lengths, yani length of this part plus this one, etc. Okay. Now, in case any of the parameters in epsilon over D or Reynolds number are changing, then I should compute for each part its own friction factor. So please pay attention for this. Okay. Then whenever you have a change in parameter, you should get F for each part alone. And you can add together parts that have common characteristics. Yani parts having common Reynolds and common epsilon Okay, epsilon over d then can be, if you want, lumped together, because this can be written as f times sum of lengths over d. Again, I repeat, if same characteristics of epsilon over d and Reynolds are satisfied. Now, in case it's not, I should divide the system into several parts, and for each part, and if you have, let's say, two parts of different characteristics, you do f1 L1 over d1 times v1 square over 2g, plus for the second part you do plus f2 times L2 over d2. Okay, so then you should do the calculation for each part alone. If the Aslan, you can deduce from this expression that if you have same v and same d and same roughness, so and f will be the same, you can take it into fact. In case it's not, you cannot take into fact. Okay, so in case, as I repeat, I have a change in any of the parameters affecting the friction factor, you should compute f for each part. In case they are sharing same characteristics, same diameter, same average velocity, same roughness, you can take f into factor, and yes, then it's f times sum of L having same characteristic over d times v bar, which will be common between them because you have same characteristic, over 2g. In case it's not, we divide it into parts. So this is for major losses. Now, what about minor losses? Any fitting that is present in the flow will induce losses. So whenever you have a valve, if you have a bend, okay, if you have a sharp exit or an inlet, all of these are sources of losses. And these losses can be computed from tables because we define what is called the loss coefficient K. This is found from a table. And if you know K, once you get K from the table, you can say that for a certain fitting, the minor loss is K times V square over 2G. Okay. So now, because both major losses and minor losses are multiplied by V square over 2G, then you can take V square over 2G by as a factor, and inside you have FL over D, which consider the major losses, plus summation of uh, coefficient related to minor losses. So for example here, what is sum of K in this example? In this example, what are sources of losses? First, I have an inlet. Whenever you have an inlet or exit, you have a coefficient of loss related to it because you have sudden expansion or sudden contraction of your flow. Whenever you have sudden expansion or sudden contraction, this will lead to loss. And even if you have, of course, if you have smooth transition, the loss will be reduced. But each fitting, and you have, for example, this is a device for smooth transition, but also it's characterized by a certain loss. So they will give you then for this expansion fitting what is coefficient K. Okay, so here you have K at inlet, K1 at inlet. You have you can get it from a table. You have for the open globe valve a certain coefficient K. This is K2. The pump will be, you should add for the pump, how to take it into account? You should add plus H pump for your P1 over rho G plus V1 square over 2G plus Z1. Should add plus H pump. Okay, so this is how you account for the effect of your pump in your energy equation. Now, you have here a bend. Whenever you have a change in direction in the flow, you have losses. So you will go to your table, you will look at a bend radius of a 12-inch bend radius will result into which K. So you have K3, get K3 from a table. You have an elbow here. So the purpose of the elbow also is to uh, join two pipes of different directions, doing 90 degrees. So you can get K4 from the table. You have also here a half open valve, you get K5. So all of Ks will be found in tables. and tables will be provided for you. And at the exit, you have a certain coefficient K. So in total here, you have 6 sources for minor losses: the inlet, the open globe valve, the bend radius, the regular elbow, the half open gate valve, and the exit. So you should sum all of these Ks. And again, here, please pay attention for something also. In general, okay, when you have, for example, an inlet, K coefficient is related to the velocity after the reduction. So here, okay, while for the exit, the velocity V you multiply by is the velocity before the expansion. So always in the table or in the graph they give you, they will tell you K is multiplied by which velocity. But now I'm telling you, whenever you have an inlet, K is multiplied by the velocity after the contraction, because here you have a large reservoir and suddenly you have motion in a duct. So you multiply for an inlet K by the velocity after the inlet, while for the exit, you multiply K by the velocity before the exit. Okay, so here it's a common velocity V. This is why we have considered it into factor, because the cross section, once you start from this point to the end point, you have exactly the same velocity. In case D is changing, you should pay attention, okay? And if, for example, if I have an expansion like this, I have change in diameter, then the expansion fitting coefficient K in general is related to the second velocity. They will tell you this in the table. It will be clear. I will show you tables. They will tell you, for example, this coefficient is multiplied by velocity after or by velocity before. They will tell you. So you will know this K should be multiplied by V before or after from the graph. And then you should pay attention then to change V. So when you work with the first part, you take V1, let's say. When you work with second part, you take V2. And to know if the fitting loss should be accounted with V1 or V2, you look at your graph. The graph will tell you if it's relative to the velocity after or before. We'll see this in examples to understand. So, for example, you will find in tables for different fittings what will be the value of K. This is an example, for example. You can have a table, you can have a chart. This is a chart giving you K. As I told you, for example, here, okay? For example, here you have 2 possible cases. You have sudden expansion, you have sudden contraction. And as you can see here, they specified for you that for sudden expansion, the velocity of reference is the velocity before the fitting. Yani if you have an expansion and you want to use this graph, the minor loss of the expansion should be taken with the first part, because I'm multiplying it by V, velocity of the first part, not velocity of the second. However, if you look at this other graph of the contraction, of the sudden contraction, they told you that the velocity multiplying related to the friction coefficient is after the contraction, is for the second part. Okay, so this is how you know if I want to account for losses, if I take it for this part or for this one. Yeah, example. You have a sudden expansion. You have a duct of length L1 here and a second part of length L2. Okay? And you have different diameters. You have D1 and D2. Of course, here, since D is changing, you cannot take one friction factor for both. So you should calculate a friction factor for part 1 and a friction factor for part 2. So if you want to put the expression of all losses here, you should do sum of major losses, H major, plus sum of, so H friction total is equal to sum of H total is sum of major let's call it هن عادة ال HF بيخلوها للميجر loss و H total هي الميجر plus minor. اوكي H major عادة السيمبل تبعها HF and H minor السيمبل تبعها HN. okay now in this example مثلا what are the major losses, what are the minor losses? If you are going from this point to this one, first you have two parts. You have L1 and L2 and they are characterized by different diameters. So I might have a change in Reynolds number. So F can change. Okay, this is why I should find F1 and F2. So major losses will be written as F1 times L1 over D1 times V1 square, V1 average square over 2G. Okay, so this is losses related to the first, major losses related to the first part, plus major losses related to the second part, plus F2 times L2 over D2 times V2 square over 2G. When we deal with turbulent flows, okay, we have, you know how to get this V average. V average is Q over A. So to get this V, we need the flow rate. We divide the flow rate by the area. Okay, this is V we are talking about. Now, when we want to compute the value of minor losses, we should add the minor losses. Here, we go to the figure. The source of minor losses is the sudden expansion. But as they told us, the coefficient K of the sudden expansion is defined relative to the velocity before the expansion. This is V we consider. This is why we should add here a plus K. So here it's plus, so plus K times which V times V2 square over 2G. Sorry, V1 square, because as we have seen in the figure, it's relative to the velocity in part 1. Okay, so it's K V1 square over 2G. While if you consider the following figure, they told us that K is defined with respect to the velocity after contraction. So then you will put here what will change between these two cases is that in the second case, instead of plus K V1 square over 2G, it will be plus K V2 square over 2G. Okay, so always to know which velocity to use with K, you go to your graph. So for sudden expansion, in general, هن بياخدوا الvelocity الأصغر. This is why بالexpansion أخذوا velocity before, sorry, velocity الأكبر, يعني corresponding to the smallest area. While here, they considered velocity after contraction because V will increase here. So this is why for the inlet, for example, they consider the characteristic velocity للcoefficient of loss هي velocity after الانلت، لأنه هيدي V أكبر من قبل، لأنه قبل كانت الاريا كتير كبيرة وفجأة صارت أصغر. بينما بالexit بالعكس، بالexit if you have exit to a reservoir أكيد هون V بتصير أقل بكتير، باخد V before. So always in general we take V higher, the highest V. In case يعني in general it will be clear بالgraph. Okay, but in case they don't give it to you, خدوا ال K relative to the highest. Okay, so this is about losses. Okay, now each type of fittings حيكون عنده أو table أو graph. مثلا هون you can see that depending on the angle of the band, the value of K will change. So here, for example, they show you for different angles of the band how my coefficient of loss is changing. So the loss coefficient is depending for a band, is depending on the angle of the band, and is depending on the ratio of the radius of the band over the diameter of the dot. So these two parameters will affect K. So in general, for example, if I give you R over D equal 10, and the radius is 9, and the angle of the band is 90, you go to this graph and you say, I will take R over D equal to 10, theta equal to 90. I can read the value of K. So it's nearly 0.33, nearly. Okay? So this is how you get your loss coefficients from tables or graphs, and then you can replace in the energy equation the values of these cases. So this is an example. Okay, again, the same example. We are repeating it. We can see here different sources for minor losses. So we should go to our table and get for all of these. And here you have also this, of course, we should add it. So we should go to tables and see what are the losses induced by these different fittings. Okay, and then you can compute the total friction head as the addition of major and minor loss. So this is the material of this chapter, but this chapter really requires practice. And it's very simple if you practice on it. So we'll do examples, okay, together on this chapter. If you want, if you can continue with me now, I can do a live example for you. If not, I have a lot of videos as usual on review problems, so you can go over them. And Wednesday we do an extra session for your questions. So do you prefer to start now with examples, or you want to go again over the material and over the review problems that I will post for you, and we go for questions on Wednesday? So what do you want to do?
دكتور بس فينا نمرق one example بقى
Yes.
هيك على السريع لنفهم.
أكيد. Of course we will. Yeah. So
Thank
let
you,
me open the problems of this chapter. So chapter 8 problems. And also I will open also على blackboard محطوط لكم كل الcharts. هلا I will show you all charts that we'll use to solve the problems. Okay. Let me open the Okay, look, in these problems you have different examples. كل example will illustrate for you يعني a certain case. لأنه عندكم هون بهذا chapter different possible cases that you might encounter. Okay. هجرب أعملكم problem في كل القصص اللي حكينا عنها. And then you will have solution for everything here. Okay, بدي شي يكون في كمان في minor losses. Okay, this is, I think, a good problem. Okay, so we have water at 60 Fahrenheit characterized by mu equal 1.21 times 10⁵ feet cube per second is to flow from reservoir A to reservoir B at a flow rate of 26 feet cube per second, as shown in the figure. The system contains a sharp-edged entrance and 4 flanged 45 degrees elbows. Okay, so first, this problem involves major losses and minor losses, and it's a problem that is challenging because the diameter is unknown. Okay, So how to think whenever we have such problem? The first step to do is to write, as I told you, equations of continuity and energy. First, because if you follow your flow as it's entering the duct, you have same diameter. You don't have a change in diameter. Okay, this implies that because you have steady application, you know that m dot n, if you want to calculate m dot here, is equal to m dot out. Okay, so m dot n equals to m dot out equals to, now you know that the expression of m dot is rho times cross-sectional area times v. So m dot n is rho a n v n, and m dot out is equal to rho times أكيد v average. Okay, rho times a out v out. Okay, now V out average. Now first it's water, so it's incompressible, rho will simplify. The inlet cross section and the outlet cross section are equal. أصلا everywhere the section is not changing لأنه you have 1 pipe diameter. So the cross sectional area is the same everywhere. This means that V average in the duct is constant. Okay, so this is what you can get from continuity equation. Now please remember that in Bernoulli equation V1 و V2 منن average velocities. V1 و V2 هن على streamline. يعني أنا هون إذا بدي ألحق streamline, always remember البرنولي والgeneralized Bernoulli هي along a streamline. Okay, now in case مثلا in case I'm considering مش 1 و 2 فوق, يعني إذا عم باخد هون وهون مثلا V1 و V2 ليش فيني أخدهم equal to V average؟ لأنه ليكم بس يكون عندكم turbulent هون in general. okay, we assume turbulent flow. إذا ما كان turbulent بالcalculation بنتأكد آخر شيء. when you assume turbulent flow, for turbulent flow نحن شفنا إنه عادة البروفايل كتير قريب للفلات بروفايل. This is why if you apply Bernoulli بturbulent flow you can assume إنه إذا عم باخد V على الستريم لاين هون V1 هون و V2 اللي هي على السنتر لاين, فينا نعتبر إنه V1 و V2 على السنتر لاين nearly equal لل V average. أوكي, ليه؟ لأنه بالturbulent flow the profile is nearly flat. إلا إذا هن عطوني بروفايل. إذا هن عطوني بروفايل وبقدر جيب في average و في center line, ساعتها ما في لزوم أعمل هالassumption. بس if they don't tell me anything وأنا I consider turbulent assumption, I can consider إنه V streamline بقلب الduct هي equal ل V average because of the profile which is close to the flat profile. اوكي, هلا هون ما عندي هالمشكله لانه عم بلش ب1 هون و2 هون. يعني انا على الفري سيرفيس للريزرفوار. على الفري سيرفيس للريزرفوار the velocity is 0. اوكي, so ما عندي مشكله ب V1 V2. V1 is 0, V2 is 0. كمان P1 1 and 2 are exposed to the atmosphere, so P1 gauge انتم بتعرفوا ببرنولي أو اثنيناتهم بكتبهم gauge أو اثنيناتهم absolute. So it's the same case. إذا عم باخدهم absolute بيكون في atmospheric they will cancel out, and if I'm considering gauge pressure they are equal to 0. So a lot of simplifications can happen here لأنه عندي V1 0, V2 0, P1 gauge 0, P2 gauge 0. شو بقى عندي؟ بقى عندي Z1 Z2 elevation والlosses اوكي. هلا هون ما في pump ولا turbine فما في HP و HT, بس لو كان في pump مثلا, اذا في pump هون شو بيصير؟ بنزيد plus HP على